Hi, I'm Jeff Duffy, the DocumentDB Specialist Solution Architect, and today I'd like to talk to you about migrating to Amazon DocumentDB with MongoDB compatibility. The AWS purpose-built program is designed to help customers choose the right database for their workload. AWS provides database services in order to serve a number of needs, including relational databases, key value, document, in-memory, graph, search, time series, and ledger. And today I'd like to talk to you about DocumentDB, our document database offering. So today I'm going to introduce Amazon DocumentDB. I'm going to talk about the DocumentDB architecture, and then explain how to migrate your MongoDB workloads to DocumentDB, including best practices. DocumentDB is a fast, scalable, fully managed MongoDB-compatible database service. And DocumentDB is very fast. We can serve millions of requests per second across our read replicas. It's efficient because our unique architecture allows your instances to do more work. DocumentDB's architecture is optimized to minimize the amount of I/O that your instances send to the storage layer. And our flexible architecture allows you to scale your cluster up and out in minutes. DocumentDB allows you to add up to 15 read replicas to your cluster, which allows you to scale out effectively in minutes, regardless of the size of your storage. You can also scale instances up in minutes, going from 16 gig to 768 gig of memory in a single instance. Our storage auto scales and grows from 10 gigabytes to 64 terabytes in a cluster without any action on your part. And we offer load balancing for reads across read replicas. DocumentDB's pricing is pay-as-you-go, so you only pay for what you need when you need it. We support automated failover and recovery, promoting primaries to replicas in the event of an instance failure. Our backups are automated, and we offer point-in-time recovery, streaming changes to Amazon S3. Our storage tier is fault-tolerant and self-healing, and it replicates your data 6 times across 3 availability zones. Amazon DocumentDB is MongoDB compatible, and we are compatible with the Mongo 3.6 API, which means that you can use the same drivers and tools that you do today with Mongo with Amazon DocumentDB. DocumentDB supports replica set emulation, which makes read scaling easy by just setting a change in your driver in order to take advantage of scaling reads across your replicas. And we support live migrations with the AWS Database Migration Service, which is free for up to 6 months when migrating to DocumentDB. At AWS, security is job zero, and DocumentDB implements security by default. We are VPC only, which means that no public endpoints exist for your DocumentDB cluster. We support encryption in transit with TLS and encryption at rest, including with customer managed keys through the key management service. Our defaults are the safest, where best practices are implemented when you create a cluster. And we are compliant with a number of compliance programs, including PCI, ISO, SOC 2, and HIPAA. Amazon DocumentDB makes backup easy, and we support automated backups, which are incremental and continuous. Backups have no impact on database performance, and we support up to 35 days of point-in-time recovery for your cluster. You can also choose to take manual snapshots of your Amazon DocumentDB storage volume, which can be kept for as long as you need. Amazon DocumentDB's architecture addresses the challenges that are experienced with traditional database architectures. In a traditional database, your architecture is monolithic, where your application communicates with an API, a query processor, some sort of working set cache, logging for write-ahead logging, and storage, which all tend to live on the same physical hardware. And these components will scale monolithically and also fail monolithically. So in a traditional database, if you have 3 nodes and you want to add another node to add read capacity to respond to demand, you have to wait for your data to replicate from one of your nodes to the new node before that new node can usefully serve queries, which can take a long time if your data set is large. In the same way, if you want to add a larger node to serve temporary increased read capacity, say an analytics workload, then you're again going to have to wait for that data to replicate. We had an experience with a customer recently who had a report that they ran once a week on Friday in which they needed a lot of read capacity in order to complete that report in a reasonable amount of time. And the problem that they experienced was in order to have the data available in the time frame needed for their weekly run, they had to keep that capacity all week, even though they only needed it 1 day per week. As well, when you're recovering from a fail instance, you need to wait for data to copy to the new node in order to achieve the same availability that you had previous to the node's failure. Amazon DocumentDB addresses this with a cloud-native database architecture, which separates your storage and your compute, which allows you to scale your storage and compute independently of each other. So the Amazon DocumentDB database architecture consists of your instances, which serve your read and write queries, and a storage volume, which copies your data 6 ways across 3 availability zones, which serves the read and write queries to your instances. In DocumentDB, read capacity scaling is easy. You can add up to 15 read replicas, serving millions of reads per second in just a few minutes, regardless of the size of your storage. Whether you have 5 gig or 10 terabytes of data, it takes only about 10 minutes to add an additional read replica to increase your read capacity. In the same vein, if we need to replace an instance to deal with failure recovery, we will automatically promote a read replica to primary and then create a new instance in the background in order to get you back to that same level of availability that you had before the failure occurred. And again, regardless of the amount of storage that you had, this only takes roughly 10 minutes. Your DocumentDB storage volume is architected to survive the loss of an entire availability zone, plus a copy of your data, and still serve database reads. In DocumentDB, your backups are automated and they are continuous. We stream changes from your storage volume to an Amazon S3 bucket, and at the same time, we take daily automated snapshots as well. And you always have the ability to take manual snapshots if you need to comply with requirements. For instance, say that you have to keep backups around for a year or 3 years or 5 years. You can simply take manual snapshots and they'll stay around until you remove them. Amazon DocumentDB is priced in 4 dimensions. The first dimension is your instances, and the number of instances that you have times their size will give you your hourly rate for your instances. You're billed for I/O at 20 cents per million in US East 1, and this I/O is only counted between the instances and your storage volume. So if you make read queries from your replicas that are served out of working set memory and don't need to go to your storage volume to serve the query, you are not charged for I/O. Storage is charged at 10 cents per gigabyte per month in US East 1, and backups are charged at 2.1 cents per gig per month, but you get 100% of your storage volume for free as backup. So many DocumentDB customers never pay anything for their backups. I'm often asked by customers, why don't we shard? Because DocumentDB doesn't support sharding as we have a single primary writer instance architecture. And the answer is that sharding brings along with it certain challenges that we've attempted to solve in different ways with DocumentDB's architecture. So for instance, if you choose to shard because you need to scale storage, in other words, you need to store more data than you can on a single volume, DocumentDB addresses the same approach by scaling automatically up to 64 terabytes. If you need to scale your read traffic and then are looking at moving to a sharded cluster architecture, DocumentDB allows you to simply add additional read replicas up to 15 in a very short period of time and let your application automatically take advantage of that additional read capacity. Cluster architectures allow you to scale writes by adding additional writing nodes. In DocumentDB, we scale vertically, which means that you'll increase the size of your write primary, but that happens quickly with very low impact to your cluster. So how do you migrate your MongoDB sources to DocumentDB? A successful migration to DocumentDB is going to consist of 3 phases. The first phase is the planning phase, in which you'll discover what you have and need to migrate from. You'll decide on the appropriate cluster sizing for your DocumentDB cluster to migrate to, and you'll choose a migration approach to move the data from your source to your DocumentDB cluster. The next phase will be testing, in which you'll take your chosen DocumentDB cluster size and you'll execute performance testing against it to make sure that the instance sizing that you've selected achieves the performance that you need for your workload. You should also test failover for your DocumentDB cluster. DocumentDB allows you to initiate failovers both in the console and through the CLI and API to verify that your application behaves the way that you expect during a failover. And finally, the execution phase, when you're actually migrating your data from your source to your DocumentDB destination. And of course, you're going to want to monitor both on your source and your DocumentDB destination to make sure that the data is migrating in the way that you'd expect. DocumentDB supports reporting metrics, the CloudWatch metrics, and so it's very easy to build a dashboard for your DocumentDB cluster and monitor your throughput as your migration occurs to make sure you're seeing what you expect. So the discovery phase involves understanding what your source deployments look like in order to execute your successful migration to DocumentDB. And the first element to understand is what type of deployment you're migrating, whether that's a standalone MongoDB instance, a replica set, or a sharded cluster. It's important to understand the version of MongoDB that you're running, the storage footprint that you have in terms of gig or terabytes of data, the number of reads and writes per second, both peak and average, so you can adequately size your DocumentDB cluster. And it's important also to understand what your connection rates look like, especially if you're running architectures like a microservice where you can have many applications connecting to your cluster at once. We provide guidance in our documentation for how to find each of these items from your source MongoDB. It's important to understand what, if any, upgrade requirements will be necessary for your source MongoDB before you can move to DocumentDB. So DocumentDB is compatible with the MongoDB 3.6 API, which means that if you're coming from, say, a MongoDB 3.2 or 3.4 source, you may not need to make any changes at all. If you're running an older version of MongoDB, you may have to provide several upgrades in order to reach a version in which you can execute the approach that you've selected. Mongo doesn't allow you to make large jumps in version numbers for upgrades, and so you may have to make a plan for these incremental upgrades that are required. If you're running, for instance, a 2.2.8 version, you may have to upgrade to 2.4, 2.6, 3.0, and so on. The offline approach, which I'll talk about in a moment, may not require a server upgrade in order to make a successful migration. But most customers will need to upgrade their drivers at a minimum in order to reach an appropriate level of MongoDB wire protocol to communicate with DocumentDB. It's worth noting that most MongoDB drivers are backward compatible. So if you're already using a current or newer than current version of a MongoDB driver, it will probably work fine with DocumentDB. The first set of tools that you'll be interested in using for your migration are going to be the Mongodump and Mongorestore utilities. These allow you to dump your database data and indexes to disk from your source database. The Mongorestore tool allows you to restore those data and indexes to a target database, in our case, your DocumentDB cluster. A nice feature of the Mongorestore utility is the fact that it allows you to specify a level of parallelism, so you can more quickly restore your data by having multiple worker threads restoring the data and indexes from your source to your target database. If you create your index first in DocumentDB, you'll see even a larger gain in speed because you're going to take advantage of building that index in parallel instead of building the index single-threaded as you would if you created the index after you restored the data. Unfortunately, the Mongorestore tool doesn't allow you to restore your indexes first and data afterward. It always restores data first and then optionally indexes after the fact. To help address this need, we've created the DocumentDB Index tool. This is an open source tool that is available in the AWS Labs GitHub repo that allows you to extract indexes from a running MongoDB source, check those indexes for compatibility with DocumentDB, and restore those indexes to DocumentDB before you use the Mongorestore tool to restore your data, thereby allowing you to take advantage of that parallel build of your index when executing your migration. The AWS Database Migration Service is a managed migration service provided by Amazon to allow you to easily move your data from your source MongoDB to DocumentDB. And the DMS components consist of a replication instance, which is responsible for running the processes that copy your data from MongoDB to DocumentDB, a source endpoint, which points to your source MongoDB database, a target endpoint, which in our case will be a connection to your DocumentDB cluster, and one or more replication tasks, which are the processes that copy the data from your source endpoint to your target cluster. The Database Migration Service supports MongoDB sources from the 2.6 and 3x families, and it supports 3 modes of operation. A full load, which is a complete copy of a source database to your target cluster. Change data capture, which copies only the changes that are applied in your source database to your target cluster. And a full load plus CDC operation in which all data is copied first and then changes are replicated ongoing to your target cluster. The Database Migration Service does not replicate indexes, but you can use the DocumentDB index tool in order to dump and restore those indexes before you use DMS to copy your data. DMS requires you to create a single task for every database you want to migrate. So if you have a large number of databases that you want to migrate, we recommend that you automate the process through the AWS API in order to make your migration easier. DMS is free for up to 6 months when migrating to DocumentDB. So there are 3 basic approaches that you can take to migrate your source MongoDB to your target DocumentDB cluster. They're the offline, online, and hybrid approaches, and each provides trade-offs between the amount of downtime that your application will experience, the complexity of executing the approach, and the speed with which your migration will occur. And choosing one has a number of factors that go into it. But for instance, if your application is a dev test migration, then more downtime may be acceptable in order to achieve a higher rate of throughput and therefore a faster migration. But if you're moving a production application, then minimizing downtime will be your primary concern. The offline approach begins with your application ceasing writes to your MongoDB source. You'll then dump your data and indexes from the MongoDB source with the Mongodump utility. And you'll optionally pre-create indexes in your DocumentDB cluster with the DocumentDB index tool. You'll then restore data with the Mongorestore utility to your DocumentDB cluster, and then change the endpoint from your application to your DocumentDB cluster and resume operations. This is the fastest method, as dump and restores are typically the fastest way to move data from a source to a destination. It is the simplest approach, as it only requires 1 or maybe 2 tools to execute, but it invokes the highest downtime, as your application cannot write to your database until the dump and restore is complete. The online migration approach begins with your application continuing to use your source database as normal. You can optionally use the Amazon DocumentDB index tool to pre-create indexes by dumping them from your MongoDB source and restoring them to your DocumentDB cluster. You'll then use a database migration service task to perform a full load and replicate changes from your MongoDB source to your Amazon DocumentDB cluster with CDC mode. You'll then change the endpoint from your customer application to point to your Amazon DocumentDB cluster. This approach minimizes the downtime that your application experiences during your migration. And the complexity is medium because you have to understand how to use the database migration service in order to execute your full load and replication. It is, however, the slowest method, as the database migration service is single-threaded and will only use a single process to replicate your source database to your DocumentDB cluster for each task. The hybrid approach achieves the best of both the offline and online approaches. It begins by allowing you to continue to use your source MongoDB from your application and dumping your data and indexes with the Mongodump tool to your EC2 instance. You'll optionally create your indexes with the DocumentDB index tool in your DocumentDB cluster, and then you'll use the Mongorestore utility to restore that data to your DocumentDB cluster. You'll then turn on replication with CDC mode in a DMS task from your source MongoDB database, and then change your endpoint from your application to point to your DocumentDB cluster. This approach is faster than the online approach because it makes use of the Mongodump and Mongorestore tools to dump and restore data in parallel. But it still minimizes your downtime by allowing you to continue to write to your source database until you've reached an acceptable level of replication lag. It is, however, the most complex approach as it uses a number of different tools in order to execute your migration. If you're using the hybrid approach to migrate from your MongoDB source to your DocumentDB cluster, it's important to consider the size of the op log on your MongoDB source. The op log is a continuous ring buffer of changes that occur to your MongoDB source and can be changed in size. The default size of your op log may not be big enough to ensure that all of the changes remain in the buffer while your changes are dumping and restoring from your source MongoDB to your destination DocumentDB cluster. So it's important to check the size of your op log and resize it as necessary to ensure that there is sufficient time to execute your hybrid approach. Customers often ask me if it's possible to migrate from one VPC to another. And the answer is yes, using the VPC peering facility. You simply create a VPC peer between the VPC containing the MongoDB source and the VPC containing your target DocumentDB cluster, and communicate over the peer using either your EC2 instance or your DMS task or both to move your data from your MongoDB source to your DocumentDB cluster. If you're migrating from an on-premise MongoDB source, one option is to use a VPN connection so your DMS task and your EC2 instance can communicate with your MongoDB source. You can also use the AWS Direct Connect service in order to migrate your data, which is a popular option for customers who have a large data sets to move and need the low latency and high throughput of Direct Connect. It's important to consider when planning your migration the sizing of your DocumentDB cluster. And the first consideration that you'll want to think about is availability. Availability has two major components in DocumentDB: whether or not you deploy instances across multiple AZs, and how many read replicas, and thus the total number of instances available in your DocumentDB cluster. As you can see from the chart here, depending on your availability goal, defined in terms of nines of availability, the number of instances that you'll select and the AZs that you'll deploy across will change. If your goal is 99% availability, a single instance will be sufficient. And it's important to consider that in DocumentDB, you can have durable data with only a single instance, as DocumentDB instances are not data bearing. Your data is stored in the storage volume. If you have a higher availability goal of, say, 3 nines of availability, a single replica plus another instance in a different AZ will achieve that goal. A 4 nines availability goal will require a minimum of 3 instances, your primary and 2 replicas, each in a different AZ. You can, of course, add additional instances to a DocumentDB cluster, up to 16 total, and additional replicas may provide incremental availability improvements, but generally speaking, the 4 nines availability is the highest target recommended from the well-architected program. The next consideration for sizing a cluster is the performance required of your instances. Considering the number of CPUs available in the instance size that you select is important, as the number of connections allocated to each CPU will govern the performance that you will achieve. Generally speaking, we recommend a minimum of 8 connections for each CPU core in your instance. And of course, you can support many more connections as well. Choosing an instance with sufficient working set memory is important, as you want to make the best use of the buffer cache in order to cache previously executed queries on the instance. You have roughly 2/3 of the RAM on an instance available for working set memory, with the other 1/3 reserved for the actual engine itself. And then the read and write requirements that are necessary for your application are important to consider from a network performance perspective. If you need to be able to push a certain amount of write or read throughput, choose an instance that supports at least that amount of input from a network perspective in order to make sure you achieve the performance required for your cluster. Choosing your recovery objective is important for DocumentDB. We offer, as we discussed before, point-in-time recovery from 1 to 35 days. And setting that backup retention period will allow you to choose the recovery point objective that you can achieve with your DocumentDB cluster. Backups are retained for the retention period, and that includes the automated snapshots that we take on a daily basis. You can also always take manual snapshots anytime you like, which will be retained forever until you delete them. Customers often ask me why there is a backup window selection in your cluster creation dialog if backups are automated and continuous. And the answer is that this is the window in which your automated snapshots will be created. And the reason for those automated snapshots as a complementary backup approach is for customers who want to automate some other process based on those snapshots. A common implementation is customers who want a dev test cluster that closely mirrors the data set of their production cluster. What they'll do is during that backup window, the automated snapshot will execute, and they'll use automation to automatically create a new cluster based on that daily snapshot. So they have close to a 24-hour window where their dev test data emulates their production data. Some final planning considerations for your migration are making sure that you pre-create indexes whenever possible. Remember that Mongorestore creates the indexes after restore, not before. So use the DocumentDB index tool to pre-create your indexes to get the maximum performance for your migration. And keep in mind that the Database Migration Service does not copy indexes. So it's important to use the DocumentDB index tool to extract and restore your indexes as well. Make sure if you're doing a hybrid migration that the oplog is of a sufficient size during your testing phase to retain all of the changes during your migration so you don't lose any data. And finally, if you're migrating from a sharded cluster, which is essentially like doing multiple migrations from replica sets in parallel, it's important to take a couple of steps to make sure that your data is consistent. The first is to turn off the MongoDB balancer process for sharded clusters. The balancer is responsible for migrating data back and forth between shards in a sharded cluster to try to keep roughly the same amount of data on each shard. It is possible for a data move from that balancer to fail, and if that happens, you'll leave what are called orphan documents behind on the targeted shard where the failed move occurred. In order to make sure that you have a consistent migration, turn off that balancer and then run a command on each shard to clean up those orphan documents. We provide guidance for these commands in our migration documentation. Let's perform an offline migration. We'll start by creating our Amazon DocumentDB cluster. Then we'll install the tools on an EC2 instance used for migration, including the Mongodump, Mongorestore, and DocumentDB index tool. Then we'll use the Mongodump tool to dump data and indexes from our MongoDB source. We'll use the DocumentDB index tool to check those indexes for compatibility and then restore them to our DocumentDB cluster. Finally, we'll restore the data using the Mongorestore tool, making sure to use the correct settings for maximum performance. Our demo cluster is going to have an availability goal of 4 nines, so I know that I need 3 instances, 1 primary and 2 replicas, each in a different availability zone. I also need 30 gigabytes of working set memory for each of my instances, and my recovery point objective is 30 days. Let's create our DocumentDB cluster. We'll start by going to the DocumentDB console. We'll click on the Create button in the upper right to create a new cluster. And I'll name this cluster Demo Cluster. For the instance class, I'll select a DB-R4 2x large because I need 30 gig of working set memory, and that 61 gig, 2/3 of which will be working set, will give me roughly 40 gig to work with. I'm going to leave the number of instances at 3 because that's going to give me the 4 nines of availability that I'm looking for. We'll go ahead and set our master username and password for the database. And we'll show our advanced settings. We'll leave this cluster in our default VPC with the default security group. It's just important to note that your EC2 instance for migration must be able to communicate with your cluster. I'll leave the default cluster parameter group enabled because I don't want to disable TLS for this migration. And we'll leave encryption at rest as it is. We're going to set our backup retention period to 30 days to meet that 30-day recovery point objective that I need. And we can leave the rest of the settings as they are and create our cluster. While our cluster is creating, let's install the tools we need for the migration on our EC2 instance. I'll begin by installing the Amazon DocumentDB index tool, which I can find at the AWS Labs Amazon DocumentDB Tools GitHub repo. I'll go ahead and copy the URL I need to clone the repository. On the EC2 instance I'll be using for the migration, I'm going to use the Git tool to clone the contents of the DocumentDB index tool repository. Looking inside the contents of the cloned repository, I can see a file with the name requirements.txt. This file contains the dependencies needed by the tool in order to export and restore indexes. I'll use Python's pip tool to install these dependencies, and I can run the tool with the help option to verify it's installed correctly. Now I'll create the yum repo file on my EC2 instance so I can install the correct version of the MongoDB tools and shell. And now I'll use the yum tool to install the MongoDB tools and shell. Now I'll use the Mongo shell to connect to my source MongoDB replica set. We can show the database is available, and we're interested in the one named archive. Then let's look at the collections in archive, and we can see that I have one collection named tweets. My tweets collection is of a decent size, and I can see that I have two indexes defined. Looking at those indexes, I can see that I have the default ID index, and then another index with a key on favorited. Now I'll use the Mongodump tool to dump data from my source database. I'm going to just dump the archive database. And note that I have to specify that I want to authenticate against the admin database. If I don't, the Mongodump tool will attempt to authenticate against the database I'm dumping. Now that I see that my tweets collection from my archive database is starting to dump to disk, I'll use my time machine to jump ahead to the end of the dump. Once my dump is complete, I see a new directory named dump. This is where Mongodump by default puts my data and indexes. And in this dump directory, I'll notice a new directory named archive, which is the name of the database that I've dumped. In this directory, I'll see two files, tweets.bson, which is the actual data dumped, and tweets.metadata.json, which is the metadata definitions of my database. And if I look in that metadata file, I can see the indexes defined, including both my default index and the favorited index. Now that I've dumped my data and indexes, I can use the Amazon DocumentDB index tool to check for any compatibility issues in my dump directory. I do so by using the show issues option when I run the tool. I use the dir option to point to my dump directory, and all of my indexes are compatible. I see in the DocumentDB console that my cluster status is now available, so I can use the DocumentDB index tool to restore indexes to it. My cluster has TLS enabled, so I'll need to download the AWS Certificate Authority file to connect to it. I'll do this by visiting the documentation linked in the console and copy the link for the RDS Combined CA Bundle PEM file. I'll paste the download command into my EC2 instance and download the CA PEM file. Now I'll verify connectivity to my DocumentDB cluster from my EC2 instance by copying the connect command from the console. I'll paste the connect command on my EC2 instance and connect to my DocumentDB cluster using the Mongo shell. And now I'm connected. So we can see that I have no databases yet on my DocumentDB cluster. Now I'll use the DocumentDB index tool to restore indexes to my cluster. We can see that I'm using the connect string for my cluster, and that I've chosen the restore indexes option to restore the indexes, pointed to my dump directory, and used the CA file I've downloaded to connect over TLS. And we've pre-created both the default ID and the favorited indexes for my tweets collection in my DocumentDB cluster. When I created my cluster, I used an instance class with 8 CPUs. Now I'll use the Mongorestore tool to restore the data to my DocumentDB cluster. I'll use that combined CA bundle file that I've downloaded previously. I'll point to my DocumentDB cluster endpoint. And because I have 8 CPUs in the instance type I've selected, I'll use 8 insertion workers per collection for this restore. And I'll also use the no index restore option to avoid restoring indexes after. Now I've begun restoring my data to my DocumentDB cluster, and I'll use my time machine to jump to the end of the restore process. Now that my data restore is complete, I'll use the MongoDB shell to log into my DocumentDB cluster and verify my data and indexes are there. We can see that the archive database has been created and has data. We can see that my tweets collection now exists. And we can see that the indexes are still defined correctly for my restored index from the index tool. The offline migration is complete. Please visit the additional resources that we have to get more familiar with Amazon DocumentDB, including our Getting Started guide, the migration guide, and our documentation, which covers all of the information that I've talked about today. And finally, the recent blog we've published for migrating to Amazon DocumentDB using the offline method. Thank you for your time today, and I hope you enjoy using Amazon DocumentDB.